This is part two of ITM 560 linear models. So where we left off where we created a model, okay, using Fit2. We did the summary of Fit2, and we saw that our R-square was 0.13. However, this is using the training data set. This is where the validation data set comes into play, because the validation data set has data that the model has never seen before. So let's go through some steps to create the R-square of this model against the validation data set. So the first thing that we're going to do is that in the validation data set, we are going to create a new variable called predicted affairs. In other words, we're using the model Fit2 with a validation data set, and we are inserting the predicted values into this new variable that we're creating, affairs underscore predicted. I do that using native R, saying dataset validation LM, $, and then the variable name. So let's run this. Okay. And we can take a look at our validation data set. And here we have our predicted affairs. So here they actually have 0 affairs, but the predicted affairs are 1.6, 2.0, negative 0.42. Then if we scroll down where we have the people that actually have had affairs, let's scroll down. Let's see, where do we have people with affairs? There's going to be some people here with affairs, or not. Let's see, there's a total of 194. For some reason, this is not. Let's run this again. Validation, 194. Just sort this. Okay, here we have people with 12 affairs, and their predicted values are 3.16 and so forth. Okay, now what we're going to do is that we are going to create some values that we need. So we're going to do the mean of affairs. Okay, and we've inserted it into this object. Okay, if I run this, it's 1.6. So that means that on average, there are 1.6 affairs per person. Then we're going to create some other variables, the residual and the totals, that are basically, the residuals are affairs minus the predicted affairs, and then we square it. And the total is affairs minus the mean affairs, that 1.6 that we calculated, and we square that. Run this and see what we get. As you see, these are the little values that we're getting. And to get the R-square, we're going to sum up all of this variable that we just created and sum up all of this variable that we created. And it's 1 minus that. So let's go ahead and run this. And this gives us an R-square of 1.0. I'm looking at it here. If not, I just highlight this and run it, 0.1. If we recall, our R-square on the training data set was 0.13. Our R-square on the validation data set is 0.1. Again, this is data that the model has never seen before. And this is a true test of how well it is capturing the variance within the data. Okay? So moving on, we are now going to do something different. We are going to create the model by automatic selection of variables. So if I run this is same as Fit1. Basically, I'm predicting affairs with all the variables. So if I look at what Fit3 is, again, it's all the variables. Prior, we just said, let's just take the significant variables and create another model. There's an automatic way. There are many ways that we can do automatic selection of variables. This automatic selection of variables, we are going to use backward selection, and we're going to also use something called the AIC selection method. So let's run this and see what it does. So what it did was it went through all the variables and it started plucking out one by one. And as it plucked out one by one, it got to a point where it said all the variables removed were gender, children, occupation, education, and age. And here's our final model with an R-square of 0.13. We know this. The AIC criterion, the Aikiken criterion model, AIC, does the same thing, but with a different criterion for selecting variables. It has removed actually the same variables, and obviously if it's removed the same variables, it's keeping the same ones, and it has the same R-square. So this is automatic selection. Automatic selection is very useful because as we take out one predictor, one independent variable, all the p-values change, and something that was not significant could suddenly become significant. So now, the next thing that we're going to talk about is interactions. So what is an interaction? Let's run this. The way we do interaction is that we say whatever we want the interaction to be, but if we want to test out all possible interactions, we say give me all the variables, and we say square it. We're not squaring it, we're doing interactions. And when we see the summary, we're going to see what interactions are. So for instance, here's the model. It has gender, age, years married, everything that we know that it had before, but then it says gender times age. Gender times years married. Gender times if they have children or not. So before, gender did not come out as significant, but we may have a hypothesis that maybe gender is significant when it's interacting whether or not they have children or not. So imagine that perhaps males with children are faithful and males without children are unfaithful. It could be. It's a hypothesis and we're just testing it out. But as you see, now we have within all possible interactions, we have a lot of predictors. And so this is where the backward selection or any other selection method will become very handy. As you see, it's going through everything. Okay, it's eliminating a lot. It's going through a lot of steps. And now it has finished. Here's my final model that, again, we can try to decipher what it's saying. But the main thing is this. It eliminated all these variables, meaning age times religiousness, children times occupation, etc., etc. And it came up with a final model where the R-square is 0.252. This is almost double than the 0.13 that we had before. So with interactions, we're now creating a model that is able to explain 25.2% of the variance. Let's do the AIC method. It's going through its steps. If you have a not so powerful computer, this will even take a lot longer. And give us some warnings, but in the end, let's take a look at what it did. It created a model with an R-square of 0.257. Well, again, which model is better? Well, we'd have to just do a little bit more investigating, but it seems like this one, at least I have an argument saying that the AIC was able to eliminate enough variables to come up with an R-square of 0.257. If we want to see what was the R-square before we took out variables, we just have to do this again and take a look. The R-square is 0.329, much higher, but it's using variables that are not significant. And that's, in other words, the model is overfitting the data, the training data that it's using. And it's going to perform probably a lot worse on the validation data set. So that's why we just want to keep significant variables, and that's why we do our selection methods. And that is it for linear models.